Yeah, so can you see the screen?
Yes, sir, we can see the screen.
Good. Okay, so we'll now move on to the next topic. So far, we have been studying only combinatorial circuit. That means you have a function, Boolean function, which you implement in a circuit using gates. But that is not enough in many situations, and you need to have a notion of the memory. And a way to handle the notion of memory or sequences, where the sequence is important, is by means of a mathematical structure called finite state machines. I think most of you have studied this in your flat course, but some basic things I'll repeat. And these finite state machines are implemented using circuits which are known as sequential circuits as opposed to combinatorial circuits. And these circuits, they have memory elements, which means that they need to store the values from past instances of time. And such memory elements would be implemented using a component, as you all know, which are flip-flops and latches. We'll mainly use flip-flops. And this type of circuit, which uses this memory element along with the combinatorial element, would be known as sequential circuit, and they are very common. Any talks which involves modeling a sequence will need such a circuit. In fact, it should be told that if you try to build a computer using the original people much earlier when they started building a computer, it had basically two parts. One part was a data path, which was built using which consisted of ALU and the bus and things like that, which kind of transferred the bit vectors from one part to another, and then did some computation, maybe addition, subtraction, complementation, or comparison, even multiplication. So these are the things which ALU do, and all of these can be implemented using combinatorial circuit. But there is another equally important part to a computer, which is known as the controls. Okay, so what control does, it decides the sequence, as in a flowchart or an algorithm or a program even, the sequence in which this operation should be performed. It controls the sequence. And for this purpose, the moment you try to control the sequence, you will need sequential circuits. So all this control part of a computer, that is the second part beside the data and the ALU part, would be involving sequential circuits. Okay, so maybe we'll that how to build sequential circuit for some control inside a CPU. Those will come later. Maybe not even in this course. Maybe it will come in your next course on computer organization. But nevertheless, sequential circuits are important for many situations, not just CPUs. It is important in many situations, as you can appreciate. Okay, so I think definition you all know. What we'll talk about today is that we will talk about two equivalent, note the term, they are equivalent representations known as the Moore machines and the Mealy machine. So these are two equivalent forms of a finite state machine. Okay, I'll soon explain what is a finite state machine. Maybe I'll explain with an example of a finite state machine. Very simple example. Example as follows. Suppose you have 4 LEDs. Okay, and let's number them 1, 2, 3, and 4, LED or light bulb or whatever. And you have a switch. Which every time you press the switch, the first time this LED glows, second time this LED glows, second time. So in this sequence, 1, 2, 3, 4, and then again back to 1, then 2, 3, 4, and then again back to 1. In this sequence, they glow. Okay, so how do you mathematically represent this sequence of events? Mathematically represent meaning, if you follow this mathematical structure definition, you would be able to generate this sequence. How do you represent? You represent using a finite state machine. So what is a finite state machine? Let me draw the state machines in this particular form. So you have these bubbles, which we call as states, and you have some state numbers or rather state encodings. I will come into details of those state encodings. And then you have transitions between state. So these you can see are the possible transitions you can have. These you can see are the possible transitions you have. Okay, and there is it starts from maybe some state, maybe from state 1 it starts. And then it goes on in sequence. And when does a transition happen? Maybe this switch, I call it as I, an input I. So whenever this input is turned 1, this transition happens. So every time the input is 1, this transition happens. Note that in this particular case, the output, which is maybe the LED which is glowing, is the same as the state number. So it's here the output is the first LED glowing, the second LED glowing, and so on. It's same as the state number. So this is an example of a finite state machine. Few facts you note about this thing. First of all, you have, so what are the things you have? You have states, which are nothing but these bubbles that we have. Then you have transitions. Which are the edges or arrows or whatever you call. And then you have some input. And then you have some output. Okay. So this is a very simple example, but as it turns out, there are many more complicated examples which could be modeled by such a simple structure of a finite state machine. Okay, so so this diagram that I have called would be called a state transition graph, or a state transition diagram, or a graph, or whatever. Okay, you can probably also represent this as a state transition chart or a table. State transition table, where you will have something like this. I'm drawing it very badly. You have the present state, you have the new state, and and then you have the output, and you can have input. Like if input is something, input is say click equal to 1, you have some next state and output, and if input is 0, you have some other next state and output. If you have any other input, other columns will get added. So what do you write? It's, for example, if present state is 1 and input is 1, the next state is 2, and the output is also 2. If the present state is 1 and the switch has not yet been pressed, the next state is still 1 and the output is 1, and so on. If the next present state is 2 and a switch is pressed, the next state is 3, output is 3. Otherwise, if the switch is not pressed, it is same. So this way, equivalently, I mean, these are the same thing. You can have either a state transition diagram or a state transition table. Okay, so now let us look at, so any question so far?
Sir,
Huh.
what happens when we turn the switch on for the first time? Like at that point, then 2 will turn on.
Okay, right. So maybe sometimes you have a dummy state. Sometimes you have a dummy state and say you start with state 0, the first time you press a switch, you go to state 1. Go to state 1. Yeah, good question. Okay, very good. So as it turns out, this is a very simple task. But you can have other tasks also. For example, suppose I have a blinking LED which is like this. So if I number this 1, 2, 3, and 4, the sequence would be this 1, 2, 3, 4, then 3, 2, 1, then again 2, 3, 4, 3, 2, 1. So this and this and this, then again this and this and this, like that. So 1, 2, 3, 4, 4, 3, 2, 1. Okay, so what would be the state transition diagram look like? Can you draw it? Oh, sorry. Can you draw the state transition diagram for that? Can you suggest? So I have 4 LEDs. I have 4 LEDs.
So we
And
will keep 4 states and one dummy state as before, and then the transitions will be from 1 to 2, 2 to 3, 3 to 4, and again from 4 to 3, 3 to 2, and 2 to 1.
so you need 4 states and maybe a dummy state. Yeah. So what would be the sequence? How do I, but from 4 I need to go back to 3. So this is not correct.
Sir, we can keep 2 copies of 2 and 3, like 2 prime and 3 prime, and then make a path from 4, 3 prime, 2 prime, 1.
So you have 2 copies of 2 and 3. That's what
Yes,
you.
yes, sir. So it's 1, 2, 3, 4, and 4, 3 prime, 2 prime, 1.
What about if we try to remember the direction in which we are moving? Because from 3, if we are going from left to right, from 3 we'll go to 4. Whereas if we are moving from right to left, from 3 we'll move to 2. Isn't that? So it's a, or let me draw it this way. Let me kind of reconfigure this a little bit. Let me reconfigure this a little bit. So you have 1 and 2 and 3 and 4. So you can go this way when you go from left to right, but you will go the other way when you go from right to left. And how do you decide? So to decide, say suppose when you are 2 at 2, to move to 3 or 2, you need to decide you are going from left to right or you are going from right to left. So how can I do that? So maybe what you said is correct. I am that there are 2 copies, but I want to do it in a slightly different way. So now can you tell what are these 2 copies? Yeah. So what does these 2 copies of 2 and 2 copies of 3 represent?
So
Given
one
that
is
I
for going left to right, and one is for going
right,
right to left.
right. So I can, yeah. So then I think it's very obvious. So you have 2, maybe left to right I represent by 0, and right to left I represent by 1, 3, 0, 3, 1, and then maybe 4. So what I do? So I okay, and then I have this. So basically, I had to increase the number of states. The state encoding was longer. Okay, that's okay. All right. So now let's come back to the simpler thing. That is, you have this structure 1 and 2 and 3 and 4, and I say that, let's come back to this simple structure, and I say that okay, on input 1 I transition. Input 1 I transition. So in this case, actually the output is same as the state, but I could have also kind of separated those two. Say maybe I can write it like I'll use this convention maybe. I'll use this convention. So this is the state and this is the output. This is the state, this is the output. So this is 2, 2. This is 3, 3. This is 4, 4. And this is 1, 1. 0 has no output. 0 or maybe I put 0 as an output. Okay, and on these edges there are transitions. Okay, so okay, so this is one possible way of representing. But you see one thing, that is this the complete representation? Is this the complete representation? Or am I missing something? Or rather, let me put it this way: is this the only possible representation? Yeah, could I have represented it in some other way? Let us see. Let me come to two different ways of writing this down. So what I will do is that let me write down a slightly different way, and then you comment whether this is good or bad or same. So in another representation, what I do is I move the output from inside the bubble, inside the state, to outside the state. Okay, so see the difference here is it goes when it is in state 1, it outputs state 1, then it gets a input 1, then it moves to state 2 and output state 2. Then it gets a input 1, moves to state 3, output state 3. And whereas this alternate representation you can read as it is in state 1, then on getting an input of 1, it outputs 1 and moves to state 2. Then while at state 2 gets an input 1, it outputs 2 and moves to state 3, and so on. So do you think are these two equivalent, or what is the difference between these two? Are these two equivalent, or what is the difference between these two?
Sir, now dummy state is redundant, right? In the right side diagram. Exactly.
You don't need this anymore. Because as you have said that when it is in state 1, after a switch press, then it prints 1. So I no longer need the dummy state. So I have reduced the number of states very trivially, but I have still reduced the number of states. Okay, but are these two equivalent? Both of them will they produce the same sequence of states and outputs?
So can you please repeat why we needed the dummy state in the first place? I missed that part.
All right. So why we need the dummy state in the first place is that say initially let's say none of the LEDs are glowing. So the first time you press a switch, what should happen? So there are these 4 LEDs. There are these 4 LEDs, 1, 2, 3, and 4. Initially, nothing is glowing. Maybe I should not have. Imagine these are binary equivalent. So initially, nothing is glowing. Then you press a switch. Then what should happen? What do you think should happen? Common sense.
One light should glow.
One should glow. And so what I'm saying that when it is initially at state 0, you press a switch, then it goes to, and moment 1 glows, you are moving to state 1. You are moving to state 1 and then 1 glows. Output is 1. Okay. Next time you press a switch, moves to state 2 and outputs 2, which means the second one is glowing, and so on. So to represent this starting, just to represent that at the first press of the switch, 1 should glow, I need this. If I didn't have this, what would happen at the first press of the switch? So you are starting from here. Let's say 1 is your start state. What would happen at the first press of the switch? So what you want at the first press of switch is 1 to glow, second press of the switch 2 to glow, and so on. But if this dummy was not there and you started at state 1, what would happen if you had only 4 states at state 1? What would happen at the first state of, so what would the sequence look like? Sequence would look like 2, 1, 2, 3, 4, 1, 2, 3, 4, and so on. So this is without a dummy. And with a dummy, it would look 1, 2, 3, 4, 1, 2, 3, 4. I want this one. I want this one. This is not correct. That's why I have this dummy. Okay, it's only for the first instance.
Okay, got it.
But you see in this representation where you get the output after you get the switch input, after you get the input, then what happens? What is the sequence we get? So you are initially at state 1, you press the switch, then you output 1. Then your output sequence will be, with these 4 states only, it will be this, which is correct. So with 4 states, we don't need this dummy state. Okay. By the way, with this dummy state 1 and this 4 state 1 to the right are they equivalent in the sense that do they always produce the same output sequence, whatever be the input sequence? Are they equivalent?
Yes, sir.
Okay, it is equivalent, but one has less number of states. What is the other difference in terms of the timing of the production of the output, or any other difference you see between these two representations? Any difference you see?
Sir, sequence of output and transition is swapped, the two models. Like in the left side model, we first make a transition and then we get output. But here we first take output and then make a transition in the second one.
Yeah, first take output, then make a transition. So do you think time-wise, will be the output and input exactly aligned in the left one or in the right one? Or assuming small delays are there, will the timing, say suppose the input is coming to be something like this. This is 1 and this is 0. Suppose you get the input to be this, or in what sequence would you get the output? Is it aligned with the input? Okay, I give you one more constant. Suppose you can move from, you have a clock, and you can move from one state to another state only, let's say, at the falling edge of the clock. Only at the falling edge of the clock, you can move from one state to another. Maybe that's a property of the flip-flop that you are using to store the states. So you can move from one state, transition from one state to another only at the falling edge of the clock. Right. So now, you know the difference between sync, but the input can happen anytime. input, so it's a human being who is pressing the switch. So the switch press can, or maybe let's say that switch presses are short pulses, but the gap between them is not synchronized. They can be varying. Okay, so the output, what will be the nature of the output timing diagram in the left and to the right? State transition can happen only at the clock edge, whereas the input can come in any asynchronous sequence, not synchronized with the clock. Okay, so which one among these two is asynchronous and which one is synchronous? The outputs. If we look at the output, would the output be aligned with the clock or it would be asynchronous? Okay, tell me one thing. Suppose input comes here. You get an input here. Will immediately output change or it will wait for the next clock? So for this case, this is for case A. Say the input sequence is this. Will the output immediately change when you see the input or it will wait for the next clock?
It will wait.
It will wait for the next clock. So the output will wait whenever the input comes, whenever the human being presses the switch, I'll wait a slightly longer time till the next clock pulse comes and then I'll show the output. Okay, but what about this case? What about this case? What will happen?
So in the left also it will wait only because the output is
only?
Yes.
Yeah.
So because the transition can be made only when
maybe
there's-
yeah. Okay. Wait, then the transition. When can it be asynchronous? When I need not. So what relaxation I should do so that immediately on input it changes the output? What relaxation can I do? Yeah, you are right. I was wrong. What relaxation should I do so that immediately it should be asynchronous? I should not wait for the next clock pulse. I can immediately transition. For what change I can make? Or maybe I am telling this one to be wrong, that at every clock pulse a state change should be there. Am I telling that to be wrong? Think a bit. Okay, I'll come back. Maybe I'm confusing. Let me think a bit. I'll come back. Let us come back to the formal definition. Yeah, I'm making a mistake. I'll come back to this. Okay, so let me. Okay, so one of these is called a Moore machine, and the other one. Note that these two are equivalent. Maybe the number of states are same, but they are output wise they are equivalent. The other is called the Mealy machine. Let me give a formal definition. So any questions so far, except for this asynchronous synchronous part? I think I messed that up. I'll correct it as we go ahead with the discussion. I am forgetting the definition. Let me look at the formal definition. I'll correct it. Okay. So any other question? Okay. So let's come back to the formal definition. Okay, so a Mealy machine, I'll talk about the Mealy machine first. These are finite state machines whose output depend on the present state as well as the input. So if we see this diagram, you can see that the output, which is this, depends on the state as well as the input. Depends on this as well as this, and these two determine W. Whereas here, the output depends on only the state. it is independent of the input. It depends on only the state. So this is a very just a representational difference. Mathematically, both are the same structure. It's just a representational difference. Okay, so let us talk about the Mealy machine first. So where the output depends on both the present state and the input. So formally, you can define it as a tuple consisting of the number of states, initial state, input alphabet, output alphabet, transition function from Q cross sigma to Q itself. Okay, Q cross sigma to Q itself. Because it's the transition is dependent on the input as well as the present state, and the output function lambda, which is a map from Q cross sigma input and state to the output alphabet. Okay, so this is the simple, the usual. So basically, all I'm saying is that there is a set of states, there is an input alphabet, there is an output alphabet, there is a transition function, and there is output function. Can you tell me what is the
Sir? Sir, what is this output function, sir? Like, I'm unable to understand.
Yes. So look at this this Mealy machine. So I want to write the output function as a truth table. What will be the output function be? As a truth table, what the output function be? Let me write down this again. Yeah. So I have so present state input. What will be the, can you write down the output function? If the present state is 1 and the input is 1, what is the output?
1.
Present state is 2, input is 1, output is 2. Present state is 3, input is 1, output is 3. Present state is 4, input is 1, output is 4. Okay. Whereas if it was a Moore machine, it is a Moore machine. The state transition is defined by the input, whereas for every state there is only one output possible. What is the output function? Kind of identity function. Okay, so is that clear now? Is that okay? Yeah, please. Okay.
Sir, I have a doubt in Mealy machine that let's say from 1 we get an input 1, right? We output 1 and go to state 2. Now, if we receive an input 0, then how will LET1
so
turn?
This is incomplete. Okay. Is that okay now?
No, sir. Like, I didn't understand how.
So input 0 means the switch has not been pressed yet.
But after pressing a switch, suppose we turn it off again, then what will happen? Is that an allowed thing to do?
No, that, so yeah, that is not allowed. You press a switch, the next LED glows.
Okay.
If you don't press a switch, then nothing happens. It stays in the same state. Okay, so basically there is a self loop. Okay, so can you tell me what is the, for a Moore machine, what is the only part that will change in this definition? For a Moore machine, what is the only part that will change? Anybody? Which term, Q or Q naught or sigma, delta, which one will change?
So lambda will be Q2
lambda
delta.
Will change. It will be just Q2 delta. It's not dependent on sigma. It's just from Q to delta. So that's the difference. Okay, we'll soon see that every milli machine can be converted to an equivalent Moore machine, and every Moore machine can be converted to an equivalent milli machine. So these two are kind of two different representations of the same FSM. It's just a convention of, it's for our benefit how you write it down. In fact, not just write it down, it's for our benefit how you make a circuit to implement it. Okay, so let us take some more example. Okay, by the way, one more thing, this states, that means you are remembering what your state is usually done in the following way. So if you come to this example, so I have 4 states. So I have 4 states, 1, 2, 3, and 4. There will be something called a state encoding. Okay. There will be something called a state encoding. So this is nothing but some symbol to represent the states. So I can take a binary embedding. So maybe I can take 0, 1, 1, 0, 1, 1. No, that's not enough. Or maybe make it like this: 0, 0, 0, 1. Any encoding I can take. 1, 0, and 1, 1. Let's say this is my encoding. Okay. So how do I represent this this encoding in a circuit? What I will do, basically I'll have 2 bits, and I will say when both these bits are 0, I am in state 1, and if the bits are 0, 1, then I'm in state 2, and so on. So basically saying that what is the encoding of the states? What is the bit encoding of the states? Right. So how do I know in my previous time instant, maybe previous clock cycle or something, I was in 0, 0, or in the previous clock cycle I was in 0, 1, which is required because for this transition I have to know that previous clock cycle I was in state 1 or state 2. I have to remember. How do I do that? What I do, I have some kind of memory elements, maybe 1 for each bit, which I call flip-flops. Okay, so what these memory elements will do, if you set it to 0, and until and unless then you ask to hold it, it will hold it, and only when you ask to change it, it will change it. So once you set it to 0 or 1, and you ask to hold it, it will hold it till it give you an instruction to change it to maybe 1 or 0. Okay, so they are kind of memories. They will hold a value, and usually these are called flip-flops. There are an alternate called latches also. We'll use flip-flops, and these flip-flops, there will be 1 flip-flop per bit. So for this state encoding 1, 2, 3, 4, you will need 2 flip-flops. You'll need 2 flip-flops to store these values. Okay, so how it will do in a circuit, basically whenever there is a circuit looking at a logic for this transition, it will look at the previous values of the flip-flop. It will look at the values of the flip-flops because it is holding the value from a past in time. It will look at that value and take the decision, and that's okay because I want to look at my past, and it's holding the value of the past. Okay, so this we'll use as a flip-flop. There are different type of flip-flops. The simplest is something called a D flip-flop. Something called a D flip-flop, which is something like the D stands for data kind of the thing. So if this is your D value, if this is your D value, and you have a clear and preset which will make it 0 or make it 1, and you have a clock So as the clock comes, D will be equal to Q. Whatever is D will be there in Q. Okay, throughout the clock cycle. Okay, and until and unless you preset or clear it, it will hold this value. And Q bar will store the complement of that. It will hold this value. So this we can use. We'll later come to details of this. You have seen that something is written that at negative edge there will be a preset. So you can do a preset clear only at the edge of a clock. So these are possible, but we'll come to this more detail. In fact, there are better flip-flops. We'll discuss them in later. But for this moment, this simple memory element will be enough to represent a finite state machine. Okay, let us come to some more examples of Mealy machine. So I will be discussing Moore machine, only Mealy machine, because as you have seen that you can easily convert a Mealy machine to a Moore machine also. Okay, so let us look at some more examples of designing a Mealy machine. So one job we would like you to be good at is that given a problem, you should be able to design a Mealy machine, maybe either in the state transition chart form or on this transition graph form, whatever form, you should be able to design a Mealy machine and or a Moore machine because they are interconvertible. Okay, so here is a problem. It's kind of a pattern recognition problem. So the thing is like this, you get a sequence, a streaming sequence of zeros and one coming as input. You get a sequence of zeros and one coming at input, maybe from a communication channel or something. So your input sigma is 0, 1. Now output can be either delta, can be either A, B or C. So as you are getting the input sequence, moment you encounter this subsequence 101, you should output A. Moment you encounter a subsequence 110, you should output B. For all other case, you should keep on outputting the default value C. Okay, so now let us design a Mealy machine for this. 2 points you try to understand. That one thing is that the input stream can be possibly infinite. It can keep on coming and coming and coming. The output is finite, but it is a finite state machine in the sense that we are allowed to use only a finite set of states. Okay, and since their states represent memory, what this basically means is that you cannot have you cannot remember everything. You can remember only something about the input sequence, input stream. Okay, but the problem is that the good thing is that maybe just remembering just 4 things about the input stream is enough to produce the output. Okay, to produce the output. Right. So can anybody tell what this Q0, Q1, Q2, Q3 mean basically? And you can see I have other things. I have kind of have a state encoding for the input. I can have an encoding for the output ABC. I can have encoding. And here I have drawn the state transition diagram. Can anybody tell what is the physical meaning of this Q0, Q1, Q2, Q3? Look at the diagram. You should read the diagram as follows. These are the state numbers Q0, Q1, Q2, Q3. And on these arcs, on these directed edges, the 0 is the input, oblique C is the output. So it's a Mealy machine. So output should be dependent on the input as well as the state. So 0 is the input, C is the output, and these are the states. Yeah, now tell me, what is the meaning of Q1, Q2?
Sir, QI means that the last 2 digits, last 2 bits form the binary representation of integer I.
Right. So Q1 means you have seen a 0, 1 so far. You have encountered a G. You are trying to remember what you have seen in the past, and you have seen 0, 1. Q2 means
we have seen 1, 0.
We have seen 1, 0. Okay, and Q3, what will Q3 mean? So let us try to see what is happening. Suppose I am at the start. I'm at the start and I get an input as 0 What does it mean? I'm looking at this arc. I'm looking at this arc. I am at the start. I am at Q0. I get an input of 0. What does it mean? That means I am not expected to see this 101 or 110. I'm still at C. Okay, I'm still at C. Suppose I get a 1. Then what are the possibilities? Suppose I get a 1. What I should do? I should now look at the next bit. If I've seen a 1, I have not yet seen the full string, so I'm still at C. But what is the possibility? What is the possibility? What is the possibility after I have seen an 1?
We can have 0 or 1.
We can have 0 or 1. So I am at Q1. At Q1, I can either get a 0. After 1, if I get a 0, I'm still at C. I have not seen all the 3. So this transition means at Q2 I have seen. What does Q2 represent? What have I seen? If I have reached Q2, I have reached Q2. What have I seen so far? If I have reached Q1, what have I seen so far? If I am at state Q1, what have I seen so far in the last state? 1.
The last one.
1. If I am in Q2, what I have seen?
1, 0.
If I am at Q3, what have I seen?
1, 1.
1, 1.
Okay. So if I am at Q2, that means I have seen 1, 0. So if I receive another 0, another 0. If I received another 1, then what should be the output?
A.
A should be the output. And what should be my state? What is the last 2 things that I have seen?
0, 1. So Q1.
0, 1. So I'm back to Q1, and I have output A. Okay. And if I have seen a 0 at Q2, so I have seen 1, 0, and then I have seen a 0. So what does it mean? What should I do, and what should I output? I am at Q2.
Output C, and last 2 symbols that will be 0, 0. So
I'm back to Q0.
Yes.
I'm back to Q0. Okay. So suppose I am at Q3 and I have received a 0. So Q3 means I have seen 1, 1 so far. I have received a 0. What does it mean? What should I output? What should I output?
B should be output because 1, 1, 0 will be last 3 symbols.
Right. And what should be the next state?
Q2.
Q2. Why Q2? Because I have seen 1, 0. The last 2 digits of this, I have seen 1, 0. Okay, so this way you can build the state transition gram. So if I use this encoding, I can. By the way, can you fill up this chart? What would be the first entry of this chart? So let me tell you what this chart means. So this is the present state. This is the new state and output. Given the input is 1. And this is the next state and output given the input is, here it is given the input is 0, here given the input is 1. Okay, so you start from Q0 as the present state. What is the next state? If Q0 is the present state, and depending on how should I fill up this chart? Next row of this chart. What should be the second row of this chart? In fact, there is nothing like second row or third row. But anyway, what is the second row of this chart? Anybody? What is PS of the second row? Q0. What is NS for input 0? What is NS for input 0?
Q0.
Q0. What is output?
C.
Okay, fine. So this way you can fill up. So what I have done in the next diagram is that instead of Q0 and this A, B, C, D, I have written down the encodings. I have written down these encodings. Okay, so what we will next ask you to do is to, suppose I have a flip-flop. Okay, so suppose I have not one, I have two flip-flops. Then what would be a circuit to represent? So you can think of this as a truth table. So PS to NS, this is a truth table. This is a truth. In fact, this is two truth tables actually. O versus PS, this is another truth table. So what are the independent variable? It is 0, 0 present state and input. Yeah.
So why is it 0, 0 for C?
Is it a 0, 0 for C? Oh, yeah. Well, there is no answer to that. It's arbitrary. It's arbitrary. It's up to you what you want to represent. It's completely arbitrary. Okay, there's no particular reason. So that's the whole idea. The encoding is completely your choice. You can do whatever you want to do. But usually people do things that helps you in your design. That helps you in your design.
No, sir. I mean, how is it 0, 0 from the Moore machine diagram, state diagram?
No, your question is why is C 0, 0? No, what is the question?
Yes, sir. I mean, how is it supported by the Moore machine? So the state machine diagram.
Why it can't be supported?
I mean, for A, B, it's 0, 1 and 1, 0, like the last two states. But for C, it's not.
No. See, all I am trying to say is that what I will do, I will output 2 bits. This entire machine will output, if you think of it as a box, the box has 2 output pins, which are 2 bits. Whenever the output bits read 0, 1, I will say that the output is A. Whenever the output bits are 1, 0, I will say the output is B. Whenever the output bit are 0, 0, I will say output is C. So that's my convention. No particular reason. So that's the choice I have made. I mean, so are you talking about the implementation problem or representing this in the thing? What?
Representing.
Okay, so if I want to modify this diagram, what I do, I replace C by 0, 0. I replace A by 0, 1.
Oh, okay, that's okay. Got it.
Okay, that's it's like I could have written ABC in my C program. It's a ASCII character, but okay, I'm working with bits and digital logic, so I cannot write ABC. I'm writing 0, 1 or 1, 0 or 0, 0. That's
because I got confused. I thought it's something else. Okay, thank you, sir.
Okay, so if you look at this table, it is nothing but a set of truth tables. So you have present state 0, 0, input 0. So it's 0, 0, 0, and the output has 2 bits. So one truth table for the first bit and another truth table for the second bit. Sorry, the next state has 2 bits. Similarly, the output has 2 bits. So all of these you can write them as a number of truth tables, and you can have the Boolean formula for each of these truth tables. And so basically, these transitions will be nothing but these conditions, that under what condition it should move to Q1 or Q2. These are nothing but some combinatorial circuits. Okay, just a minute. Or okay, fine. Okay, so that's the thing. We'll come to the detailed representation. Okay, so let us come to another example which you can do. Another example